Okay, kids, time to hear a joke. One day, there was a little bunny rabbit, and the bunny rabbit wanted to go to the museum. So the bunny rabbit hopped to the N train, took it all the way to Penn Station, switched to the B, went up to 81st Street, and went to the Museum of Natural History. Hopped in, and there was a nice museum curator all by himself. There was no business, everyone was home, hiding from the pandemic, so no one's at the museum. And they went to get to see all the nice sights. They saw the big blue whale. It was really scary. It was going to squish the bunny. Not really. They saw the bunny's relatives, like the capybaras and the beavers and the giant, like, extinct animals that were very, very scary. They saw the Teddy Roosevelt mural and all the animals that he shot in Africa and stuff like that. They saw all the animals and all the plants and all the fascinating stuff. It was super cool. Finally, they came to the T-Rex. There's a big T-Rex fossil. Looks super scary. They had giant teeth. you know, wow. And the bunny said, "Hey, Mr. Museum Curator, how long ago did the dinosaurs die?" The museum curator said, I think I know this. The museum curator said, "Oh yeah, T-Rexes, like this one, they died off at the end of the late Cretaceous period. So that was 65,000,003 years ago." The bunny was like, 65,000,003. The bunny was scratching its head. 65,000,003? That's a very specific number. That's a very precise number. How do you know it's 65,000,003? The museum curator said, "Well, my boss told me it was 65 million years ago when I started working here. And then I've been working here 3 years, so 65,000,003 years. That's how long ago it was." Ha 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 ha. Ha 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 ha. I don't get it. Hazel doesn't get it. Hazel doesn't understand the joke. Can you explain it to Hazel? What's so funny about 65,000,003? If the museum curator was working there for 3 years and the dinosaurs died out 65 billion years ago, what's so funny about 65,000,003? Tell me. Wow, thanks for that great explanation. Good job, guys. 65 million years ago is pretty commonly used by scientists to describe the end of the late Cretaceous period and when the dinosaurs died. But it's not actually that precise. They don't really know it's 65,000,003. They're pretty sure about the 6, but if, let's say, tomorrow there's a big study published, there was some brand new like radioactive dating done, and the 6 is true, but it was actually 64 million or 66 million, most people would be like, well, yeah, that makes sense. Okay, we'll just take that. So they're pretty sure about the 6. The 5 is a decent guess. All the rest of these digits, these zeros, they're not really zeros. We don't really know how long ago dinosaurs died out. And it probably took multiple years, so it's probably like a range of time, but that's not important. These zeros, they don't really mean anything. Could we just not write them? Can I just say, oh, dinosaurs died out at 65 this many years ago? That doesn't make sense either. Because this says it's just 65 years, which is no good. That's like how old I am. That's not right. We need these zeros. They don't mean anything. They're not for sure definitely it was exactly 65 million years. But we need to write these zeros as placeholders. You might already know this, but this is an important idea when we discuss sig figs. The museum curator probably knows how long he's been working at the museum. It was probably pretty close to 3 years. So if you just do the math, then yeah, you'll get 65 million plus 3 is 65,000,003. But remember, this 0 is not really a 0. We have no clue what this digit actually is. So yeah, if you add a 0 to a 3, you get 3. But if you add a mystery digit to a 3, you don't get a 3. You still get another mystery digit. We don't write mystery digits in numbers. That looks kind of weird. We'll just write a 0. So even though it's been a couple years since scientists estimated or figured out that dinosaurs died out about 65 billion years ago, we don't add on like 5 more years after 5 years. We don't add in like 10 years because it's been like 10 years since I learned it. we just say it's still 65 million because it's an approximate number. And these last two digits, in fact, all these zeros are what we'll call not significant. They don't really have any meaning. This 6 is known. It is certain. It might not quite be right, but that's okay. That's how science works. Sometimes you have to adjust your your theory. That's okay. The 5, we're not totally sure. It's uncertain. But it does still tell us it's about 5. It's still our best guess. It's still some information. So it's uncertain. These are both significant. But all the zeros, they're all not significant figures. Okay. So first thing we're going to talk about is how do significant figures get created? Most numbers are not like 65 million years ago, like the dinosaurs dying out. Most of them are measurements. And even though it seems obvious, here's how to measure stuff. If I have a nice meter stick, which I put somewhere here, this is a meter stick, you can tell, because it says 1 meter. If I measure a measurement, like, how tall is my whiteboard? Can you guys see the top of my whiteboard? No, you can't. How tall is my lamb clip? It's not 1 meter. It's definitely more than 1 meter. So I'll hold my hand here, move my meter stick up, flip it around. It's definitely more than 1 meter, but I only have a meter stick, so I can't be sure how much more than a meter it is. I'm going to look with my eyes and estimate. It's about 2/10 of a meter past a meter. So I'm going to say it's about 1.2. This 1 is significant for sure, definitely. The 2 is not. I estimated it because for some reason I got a really bad meter stick that has no markings for centimeters or anything like that. So it's about 1.2 meters. Both digits are significant. What if the lamb was about here? It's a little tiny bit more than 1 meter still. I don't think it's, but I have to estimate. I'm not sure if my clip is 1 meter above the floor or 1.1 meters. So I'm going to estimate 1.0. Again, same thing. The 1s are significant because they're definitely a 1. The clip is definitely more than 1 meter above the floor. The 2 and the 0 are not certain. They're uncertain, but they're still significant digits because they're my best guess. I do have some information that is fine. So this clip, it's about 1.0 meters. I will write the 0 because I estimated that. But let me make something clear. If you just think mathematically or just numerically, if you don't really understand what I'm talking about when I say sig figs and measurements, you would say, oh, 1.0 meters, that's the same as 1 meter. That's the same as 1.00 meters. It's not the same. The way you write the number describes how you measured it. Doesn't say you measure with a meter stick or you measure with a tape measure or measure with like a laser guided rangefinder or like your phone's measurement app. It tells you how precise your measurement was. If I write it as 1.0 meters, that means I used a meter stick that I knew for sure was a meter, but I had no idea if there was a tenth or a hundredth or 2/10 or whatever. I have no idea about the next digit. If I write 1.00 meters, that means I know for sure that the 1 is correct and this first 0 is also correct. That means I must not be using a meter stick like this. I have to be using a meter stick like this that has tenths. This is a tenth of a meter, 1/10, I'm pointing at the wrong side. This is a decimeter, 1/10 of a meter. So now I know it's definitely more than a meter, and it's less than 1.1 meters. Great, good job. But I have a last zero. The last digit is uncertain. That's the way these measurements are always written. They have one uncertain digit at the end. That is estimated. So this meter stick has decimeters, but it doesn't have centimeters. So the centimeters, the hundredth of a meter, is an estimate. It's approximate. We don't know for sure, but it's a good guess, so I'll write it anyway. So there's 4 quick rules. So that's how sig figs are measured. 4 quick rules coming in at you right now. No, 1 quick rule. No, 0. X rules to be determined of how to find sig figs when you write the number. There's a whole different thing when you calculate, which you probably remember, like faint memories of from chemistry, unless you just like didn't feel like it. But these are the rules for reading a number and determining the sig figs. So these are sig figs from measurement. We'll get to sig figs from calculations after this. It's easy. 1 rule: non-zeros always significant. Any digit that's not a 0 is always significant. Easy. Done. That's it. 1, 2, 3, 4, 5, 6, 7, 8, 9, always significant. The rule for zeros is dot right, not left. And I'll write this in my lesson plan in case you guys forget. Dot right, not left. Okay, so these are 2 separate rules. They sound really similar. It's a real straightforward rule, but we have to make sure we know what it means. It's actually like oversimplified and you're going to get confused. Dot right means zeros to the right of non-zeros are significant. So dot means there is a dot. There is a decimal place. So let's say I have a number like 1, 0, 2, 0, 0.3040. Okay? There is a dot. So the rule is zeros have to be to the right. Everyone always thinks, oh, there is a dot, so zeros to the right of the dot are significant. No, that's not the case. There is a dot, so zeros to the right of non-zeros are significant. It doesn't matter where the dot is. All that matters is there is a dot. If there is a dot, zeros to the right of non-zeros are significant. So the 1, 2, 3, and 4, they're all significant by the first rule. They're not zeros. Is this 0 to the right of a non-zero? It is. Is this one? It is. Is this one? It is. Is this one? It is. All 4 zeros are significant. This is kind of a silly rule, but that's how it goes. They are all significant. And even if there was another 0 right here, is this 0 to the right of a non-zero? Even though this is non-zero, it's still to the right of the 4. It doesn't matter how far you go. As long as you're somewhere to the right of any non-zero, you're still significant. So all digits in this number are significant. 1, 2, 3, 4, 8, 9. 9 sig figs. They're all significant. The only reason this rule exists is if you were weird and wrote a 0 over here. That 0 would not be significant. You wouldn't write that. Here's a better example. 0.00500. So use the rule. Dot right, not left. There is a dot. So only zeros to the right of non-zeros are significant. The 5 is significant, always, by the first rule. Which of these zeros are to the right of non-zeros? This one and this one. These are not significant. It doesn't matter that they're to the right of the dot. That's not what the rule says. It says it's to the right of a non-zero if there's a dot. So these are not significant. This number, 0.00500, has 3 sig figs. 1, 2, 3. So that's dot right. If there's a dot, zeros to the right of non-zeros are significant, not to the right of the dot. Okay. Not left is a little more straightforward. Let's look at 9008070. Okay. So the rule was if there is a dot, zeros to the right of non-zeros are significant. If there is not a dot, zeros to the left of non-zeros are significant. And the other ones are not. So look at each zero. Is this to the left of a non-zero? Yeah, it's to the left of the 8. There's a space in between, but it's still to the left of the 8. So significant, significant, significant by the first rule. This one's to the left of a non-zero. This one's to the left of a non-zero. This one's to the left of a non-zero. This zero is not to the left of a non-zero. So by the third rule, it's not significant. This would be different if there was a dot. If there was a dot, then we don't use the third rule, we use the second rule. Is this zero to the right of a non-zero? It is. So in this case, the zero is significant. But if there is no dot, it's not. I'll write these rules down. But that's the first step, just knowing when you read a number or make a measurement, which zeros are significant. We're going to do some practice now. No, we're not. We have to. So that's fine. I'm going to write 2 practice problems on the board, and we're going to discuss how to do them with 2 more rules. Okay. 406, 490, 63.8. Add these numbers up. And then multiply 12 times 13 times 1400. And let's do a third one just for funs. Sine 30 degrees. 30.0 degrees. Okay. Should we do the rule? Now let's take a quick break before we do the rules for calculations. Let's look at this problem. Solve this problem for me once I figure out how to show it. Everyone having a nice life so far? Yeah, you guys good? Yeah, everything's going great. It's kind of hot. That's okay. I'll find. So I'm gonna prepare the rule. You guys solve this problem. Just review from our first lesson. I'm not going to go over this question. If you need to go over it, you can look back at the previous lesson, or you can ask me in class. Okay. So if we add up these numbers, that's not too hard. We can add them all up, and we'll get 959.8. But we have to think about it logically, like we thought about the museum problem, the museum question, the museum joke. In this number, this is 406. Do we know what the tenth place is? We don't know. If we did, it would be written there. Nothing's written. They didn't write 406.1. They didn't write 406.2. They didn't write 406.9. They didn't write 406.0 either. So this 10th digit is totally unknown. We don't know. Same thing here. 4, 9. These are both known. This 0 is actually uncertain. We're not sure about this 0. It might be 489. It might be 491. We don't really know. But 0 is our best guess, so it's written. Or 0 is the best guess of the person who made the measurement, so they wrote it. But we still don't know about this mystery digit. That's okay. Now look at the answer. Yeah, we're pretty sure about this 9 because we got a 4 plus a 4, and then 9 plus 6, you carry the 1. I don't have to really go over that because you guys are math scholars. There's definitely a 9 here. The 5 there is good. 9 is okay. But the 8 is really, we have no idea if this is really an 8 or not. If you add a mystery number plus a mystery number plus an 8, do you get an 8? Maybe. There's like a 1 in 10 chance you get an 8, but it could be anything. These are not zeros. They're unknowns. So we don't know this number at all. We do know that we can at least say something about the hundredths place, tens place, and ones place. They might be off, but at least we have some information, so we will write them. So we need to rewrite this number where we only have these 3 digits: hundreds, tens, and ones. So you could say, oh, just drop the 8. That's not right. You have to round to the nearest whole number that has these 3 digits, or the nearest number that has these 3 digits and not this one. 959 does have the right number of digits, just 3. But 960 is better because 959.8 is closer to 960 than 959. So that makes sense. This is not the answer though, because if you write the number like this, there's only 2 sig figs based on the rule not left. If there's not a dot, zeros to the left are significant. This 0 is not to the left of a non-zero, so it doesn't work. We need to make the dot. Now we use the second rule, right dot right. There is a dot, so zeros to the right are significant. It is significant. So the rule for addition and subtraction makes sense. You look at each digit, the tenths, the ones, the tenths, the ones, the tens, and the hundreds. If that digit is significant in all the terms, then it's significant in the answer. But if there's even a single term where it's not known or significant, you can't have that digit in your answer. I kind of messed it up. But what about this right here? There's no digit right here. Can you guys see that? It's super messy, sorry. This is 63.8. It's not 163.8 or 263.8. There's really a 0 here, but you don't really write it. This 0 is not significant, but it is known. You don't just like write 163.8 and then forget to write the 1. We know for sure that this is a 0, so we can have this digit be significant in our answer, the hundredths, even the hundreds, even though we're missing this digit here. Because we know there's a 0 here. That is certain. That's the rule for addition. I'm going to go a little faster because it's kind of like hot. That's okay. If we multiply all these numbers, we will get 2,184,000. That's it. Okay. This is the rule most people remember because it's much easier to verbalize, but it's not as intuitive as the previous one. For multiplication and division and stuff, similar things, just count. How many sig figs are there in this number? 2. 2. There's no dot, so only zeros to the left of non-zeros. These are not to the left of non-zeros, so 2. 2 sig figs. 2 sig figs. 2 sig figs. For multiplication and division, look at all the terms. Whichever term has the least sig figs, that's the number of sig figs in your answer. So round this to 2 sig figs. It could be, I missed a 0. No, I didn't. It could be 21. It could be this or this. You just pick the one that's closer. That's what rounding means. So 2,200,000 would be our answer, because it has a 2 sig figs, like the least precise term. In this example, they all have the same number, but it should make sense that you use the least precise term. If I have like 10 students and 9 of them are super physics scholars that measure super well with a super precise meter stick that goes all the way to the millimeters, and one is kind of just like, it's like 5 meters or so, like 5.2. And they add up all their measurements. I say, hey, you 10 kids, go measure the length of this block with these meter sticks. And 9 of them do a great job, and the 10th one doesn't do a great job. My answer will not be precise because that 10th person basically didn't give us enough information. That 10th person kind of messed up the whole measurement for all 10 of us, which is very sad, but it's an example, so it's okay. All right, almost dead. It's okay, we're good. Last one, sine and cosine, also like squaring, like if I was doing like 5.4 squared or something like that. You basically use the same rules. So sine of 30 is 1/2. Please never use just fractions in your answer unless it's like algebraic. You'll see later. Don't write 1/2. Sine of 30, we could say it's 0.5, but our answer should have the same number of sig figs as our question. There's no sig figs in sine. So it's 1, 2, 3 sig figs. I should have 3 sig figs. This only has 1, so bam, bam, 3 sig figs. Good job, me. Thanks.